which I must tell you, not a lot of people are watching the recordings either. So I really think this is it. I don't think people are really following asynchronously or whatever they call it. Okay, guys, so welcome to week 5. Today is going to be sort of a fun day. And I say that because the word fun is relative, but the topic we're doing today is sort of like a topic that every quantum mechanics student knows and loves. And knows how to do at the back of their hand, knows how to calculate these quantities we're going to see today. So that's going to be interesting. I have a few logistical updates. You have a problem set due for next week, which is short, but it's a good problem set because it's going to show you some good skills. And then I had asked for your topics for the paper to be due on the 26th, right? If I recall correctly. So I won't give you a problem set for the following week or the week after that. So this way you have 2 weeks just to work on that paper. I don't see the point of writing up another problem set. I'd rather you have the time to focus on that paper and really think about it and think about the topic and come and discuss it with me on Sunday. We might even spend some time next Saturday discussing your topics. That might be something I might want to do instead of doing too much new material. But I am still going to do some new material next week just because we have to keep moving along. Okay, so any quick questions from last time? Last call, then we'll get started. Okay, let's get started. So you guys have had a little bit of experience with the rotation group. And the reason I showed you the rotation group is because it lends itself very naturally to the kind of mathematical structure we'll need to derive angular momentum in quantum mechanics. Now, how is angular momentum going to be different in this quantum mechanical context? Okay, let's think about this. So those of you that have taken AP Physics C or AP Physics 1 even, you know that there's 2 kinds of angular momentum, right? There's orbital angular momentum, and there's spin, intrinsic angular momentum. What do I mean by that? What's the difference between the 2? So we know that orbital angular momentum can be written as the following way. L equals R cross P. And cross meaning the cross product. For those of you that don't, this isn't just multiplying. So this corresponds to orbital angular momentum. I'm just going to write L for angular momentum. And as you guys know, orbital angular momentum would be the angular momentum the Earth experiences as it rotates around the sun, right? That's one kind of angular momentum. We also have another kind of angular momentum, which is sort of this intrinsic angular momentum. And that can be represented with the following, that L equals I omega. And I'll just call this spin angular momentum, or intrinsic angular momentum. Intrinsic. Right? And I is the moment of inertia of a body, right? And omega is the angular velocity. So what would this correspond to? This would correspond to the angular momentum of the Earth rotating on its own axis, right? Because it has some rotation around its axis. It has some moment of inertia, which you will spend a lot of time in classical mechanics. You'll bang your head calculating random moments of inertias for bowling balls, for spheres, for rigid bodies. I've calculated many I's, many moment of inertias. And in fact, this formula actually is not complete. As you'll see if you become a physics major and you take classical mechanics, you'll see that this I is really a tensor with a lot of different components. It's not really the whole story we're not teaching classical mechanics, so I'm not going to get into it. But anyways, these are the 2 basic kinds of angular momentum. And we sort of have an inkling now that in quantum mechanics, angular momentum is going to be different, okay, because everything's different. How is it going to be different? What can we expect to see that's different? Well, first of all, we must understand that angular momentum, as our other dynamical quantities, is going to be quantized, okay? It's going to come in discrete chunks separated by a multiplicative constant, right? In our case, h bar. And it's going to come as discrete integer or half integer values, okay? So we're going to develop a really important mathematical tool today to sort of get us all of the different values of angular momentum we can get. And the tool I'm going to show you today is going to be very important for the harmonic oscillator and very important in quantum field theory. And this tool is called, I don't know if those of you have heard, they're called raising and lowering operators, ladder operators. Ladder operators are extremely important in the context of field theory when we get there, and also in the context of quantum mechanics, because they sound exactly the way I said they do. They're also called ladder operators. What do I mean? So a raising operator is going to take us up the ladder of eigenvalues corresponding to angular momentum. A lowering operator is going to take us down the eigenvalues on our ladder, right? So let's say we have a ladder of eigenvalues separated by some constant of angular momentum, right? These raising and lowering operators are going to allow us to go from one eigenvalue to the next, up and down this ladder, up and down these quantized quantities. Okay, so they're very important. Okay, great. Any questions? Have any of you not seen these before? If you haven't, it's okay. I would just look them up. They're not very complicated, but this is something you should see in just your AP physics class when you get introduced, or even just regular physics, high school physics. Okay. So let's do a very quick review of the rotation group, and let's see how we can use the rotation group, right? O3, SO3. We're going to do it in 3 dimensions today. You looked at SO2. How we're going to use this SO3 rotation group to take us to angular momentum, to build commutation relations, to do the whole quantum mechanical algorithm that we've been doing, and to construct operators, right? Because any dynamical quantity now in quantum mechanics needs an operator, right? As we've discussed. So naturally, we're going to have angular momentum operators. We're going to have spin operators. We're going to have all of these objects that maintain the same characteristics that we've been discussing, right? That they're Hermitian, right? That they are orthonormal, so on and so forth. Okay, so let's begin. So let's do a really lightning fire review of that last problem set. So we have some prime vector, right? Which is a column vector with 3 components. And if I want to see how this vector transforms from an unprimed frame, I can use this rotation matrix to take me to the unprimed frame. Okay, and you saw something like this, except you saw it written explicitly with indices. You saw the matrix equation that looked like this. X prime upper I equals R I J X J. Right? And these kinds of equations are going to be super, super important. Get used to them, get used to playing with them, get used to moving these indices around, know the differences between an upper index and a lower index, all of that good stuff, because we are going to be using these ad nauseum in quantum field theory, ad nauseum, even in special relativity. So it's crucial you understand how this comes from this. Okay, which problem set 2 takes you through. In problem set 4, right? In problem set 5, you will see something like this. You will see how we move into space-time. So these indices run from 1 to 3, right? They go 1, 2, 3. These indices are going to run from 0 to 3, and this 0 is going to correspond to a time dimension, which, if you don't know why, it's okay. The homework guides you through that. But for those of you that have taken special relativity with me, you know that time is now a dynamical dimension that we need to think about, right? Time changes from observer to observer. So this is going to be on the new problem set, and this is SO3 1. Okay? So this is sort of our basic matrix equation. These are column vectors, right? Column matrices, if you want to call them that. right? They look like this. And R is some rotation matrix. Can someone tell me the dimensionality of R? What is the dimension of the rotation matrix? What is the dimension, dim, of Rij? Can someone tell me in SO3? Right?
3 by 3.
Sorry?
3 by 3.
3 by 3, exactly. Okay, can someone tell me what the dimensionality of my lambda mu nu is going to be? Which you'll find out what the special name for this is, but can someone tell me what the dimensionality of this will be if my indice runs from 0 to 3 and I'm in the group SO31? Just shout it out if you know. Okay, it's going to be a 4 by 4 matrix, right? The dimension just goes up 1 because that's the dimension of my group. Does that make sense? Okay, you saw SO2 and your Rij was a 2 by 2 matrix and I and J ran from 1 to 2, right? So every kind of group is going to have its own structure. Okay, so that was kind of, okay, and then you also saw that certain quantities could be left invariant, right? That's in the homework, right? So this kind of object, xi upper I, x lower I, yields a scalar, right? And it's left invariant under rotations, meaning I can put a rotation onto this object and get the same scalar back. Okay, and this was all in the homework, so Gabe is going to go over it after lecture. I just wanted to sort of just make sure we're all on the same page before we extend this sort of structure. Okay, any questions about that? And it's, I mean, it was on the homework. I explained much more detail, and Gabe is definitely going to go over it. Along with those awesome Dirac delta function integrals, right? Weren't those just so much fun? Okay, I'll just rewrite that here a little smaller. Okay. And of course, we have the following identity. Right, which is sort of an important identity for orthogonal matrices. And we also have the following the vector relation, which you should be familiar with. Those of you that just started freshman physics, or those of you that have taken any physics, should know that this quantity holds true for primed and unprimed vectors, that their magnitudes are left unchanged, right? If I have a vector that's a certain magnitude and I just rotate it, it's not going to change the magnitude of the vector, right? It's just going to change the coordinate. Okay, so let's define R for a rotation in the z direction by some angle phi. This is a 3 by 3 matrix. Oh, I think I added an extra row. I'm so used to working in 4 dimensions that all my matrices are always just 4 by 4. And you know, in the homework, you wrote out the actual equations for rotation in SO2. So the same idea would apply here, right? It would just have an extra term, that's all. And please stop me if you have any questions. So now I'm going to consider an infinitesimal rotation. And Townsend has a similar argument for this, but I do it a little differently, so you know, you can check out Townsend. So I'm going to write down an infinitesimal. I'm going to consider. By the way, is that lawnmower really loud? Can you hear that? No? Okay. You can hear me clearly? Okay. Okay. I'm going to consider an infinitesimal rotation about the z-axis. Okay, and I'm going to get the following matrices. Okay, so if I consider an infinitesimal rotation by some epsilon, this is what my rotation matrix is going to look like. And you should work out why this looks like this. This epsilon is not really an angle, so this would be in the z direction. It's just some parameter, okay, that I'm moving by. Now, very interesting, you can kind of see the way to get from here to here, but it's not a direct way. It's just sort of arbitrary. So don't put too much stock in why this is a 1 minus. What's more important is the signs, okay? Okay, and then I'll write one for the x direction. This is why these notes are so handy, because no one remembers these, and we don't use these really at all. It's just to okay, and then I'll write one for y. Okay. So now that I have my infinitesimal matrices for an infinitesimal rotation by some parameter epsilon, right? This isn't really an angle. It's more of like I'm just rotating by a little bit more, okay? And by the way, it's kind of trivial what I call them, right? Because this is just some rotation by an even smaller angle, order epsilon squared, right? And what is the cosine of 1? Just blurt it out. The cosine of 1? Is that even like a fair thing to ask? I'll give you a second to think about that. Well, I won't give you the answer, but you should think about what that is to understand why I've labeled these the way I've labeled them, okay? Why these correspond to sines and these correspond to cosines and minus, well, there's no minus cosine, that's why I only have one minus sign. Okay, now what is the natural thing to do mathematically with these objects? Does anyone want to give me an idea? Like what should I do? And I'm going to rewrite them up here. But someone think about what I should do with these now that I have sort of rotation matrices that correspond to an infinitesimal shift, right? Like a tiny shift. So let's think about that. Anyone have any ideas? My budding theorists, if I gave you this set of matrices, what would you do? I mean, there's no right answer. What would your instinct be, right? So when I got these matrices, I'm like, okay, what can I do with them? So what are we trying to get at? Like, what do I want to make? make? What do I want to construct? So right now I'm working with rotations, and I might want to construct some commutator, right? I might want to construct some commutator, right? That's really the aspect of quantum mechanics that's different from, well, not different, but what gives us non-trivial results in quantum mechanics. In classical mechanics, it's trivial. All the commutators vanish, right? They're called Poisson brackets. All the Poisson brackets just vanish. In quantum mechanics, they don't. So what might I want to start doing with these? Johnson, what do you think I might want to start doing? You can't get away just because your camera's off. So what do you think I might want to start doing, Johnson? Where does your intuition take you?
We could build up to find an operator for angular momentum.
I can find an operator. Okay, you're jumping a little bit. I only have these, right? Anyone? What does a commutator do? What is it doing to my objects?
Sees whether or not the measurements are affected when you measure the rotations for each dimension.
Well, what is it? Well, that's correct. But what is it doing to the matrices? Is it adding them? Is it multiplying them? Is it dividing them by each other?
Multiplying.
Right. So I should try multiplying these and taking different combinations and seeing what kind of commutator I can get. Yes, that seems like a natural step. Okay, so let's do that. I'll save you all the algebra, which I had to do. I'll just show you what you get, but you need to verify this stuff. A lot of the stuff I'm going to be showing you today has a lot of algebra. I'm just showing you the results, so we don't spend an hour doing algebra, but you should verify some of them. Okay, so let's just see. So let's do this combination. Okay. Okay. That looks kind of interesting. And let's do it the other way. Okay. So I get some weird matrix by multiplying them. Now let's take the commutator, right? That would seem like the natural thing to do. So the reason I'm bringing this up is if you guys choose to do research with me, you have to feel freedom to play around with the tools, right? You have to kind of have an inkling of where you want to go with some structure, and then you need to kind of create where you want to go with it. Where do you want to take the mathematics? That takes experience and that takes practice. So that's why we're doing this. So we can kind of get a feel for how these things work. So I'm going to erase these and I'm just going to write the commutator. Okay, so it turns out when I take the commutator, I get this. Which is just my RZ rotation matrix, but in order epsilon squared minus 1. Okay. So this is interesting. This actually suits our intuition, right? we've used rotation matrices to construct some kind of operator now, right? That we can sort of use in the infinitesimal regime. And why is this so good with our intuition? I mean, even in classical physics, angular momentum, or rotation, sorry. Rotations, we're only working with rotations right now. We're not up to angular momentum yet. Rotations don't commute, right? In classical physics, rotations don't commute, right? If I rotate in this direction and in this direction, it's not the same as going backwards, right? You're gonna end up in a different position, right? So rotations don't commute in classical physics either. So we need to just realize that this is nothing else but a classical realization. I've done no quantum mechanics yet. I've just sort of done some classical physics here, just in a way more abstract way. Okay, great. So now let's construct a rotation operator, okay? On some state, some rotation operator, we'll call it D of R on alpha, okay? Now, why did I call this D of R? It's because I think historically the German word for rotation started with a D. I think it's like Dahlrung or something like that. And I took German in high school, which shows you how much I've forgotten. But that's why historically this is called D of R. So you'll find it sort of labeled in all the, because you know, German was, all the physics was in German in the old days. So, you know, they had a monopoly. Okay, now we can define an infinitesimal operator in the following way, just using what we extracted. Sum 1 minus I G epsilon. Okay, and where G, so from classical mechanics, we can get all of these relationships, and G is my operator, and I'm going to have G go to some new J operator, in some dimension over H bar. K is just some arbitrary dimension. No, K is really corresponding to Z. Let me just write Z. Okay, and epsilon, my infinitesimal parameter, is now going to go to d phi, which now corresponds to some infinitesimal angle. For your calculus, for the calculus students here, you know differentials are just infinitesimal parameters, right? So d phi is now some infinitesimal angle. And I get this relation simply from here, right? And don't worry about the i's and the h bars. You know, they're just there for normalization and that sort of thing when you're doing computations. Okay, so now I'm building up my apparatus, right? These j's are now our angular momentum operators. They're Hermitian, they're all that good stuff, or orthonormal. Okay, and now we're going to do something nice. Can I erase this? Did you guys get all of this? Are we good? Okay. Okay. Can someone remind me, those of you that have read Townsend, does Townsend do something similar to this, like early on in the book?
It gets the angular momentum operators in chapter 3, but I think it goes a different route. It doesn't like.
Not like this, not with infinitesimal. Okay.
Oh, it does do infinitesimals, but it doesn't explicitly write out the 3x3 rotation matrices early on.
Oh, okay, okay. So no SO3. Okay. Yeah, I always like to have more of a group theory slant on things, just because as a theorist in general, any theorist, everyone is using group theory all the time. And so I just want to sort of implant that now because the group theory gets hard. I was showing a few of you guys, like I have a whole textbook just on group theory. so it's a deep subject. It's just that I just want you to get used to the language people use. Okay, so let's do something interesting. We'll construct this kind of operator on some unit vector n hat, and we're going to move it by some infinitesimal angle d phi. And so this corresponds to just the following construction. So 1 minus I j dotted with n, because it could be in any direction, over h bar d phi. Okay, so now I have some arbitrary unit vector. The angular momentum operator is going to be in any direction based on the component. That's why it's the dot product, right? So jx goes with x hat, jy goes with y hat, jz goes with z hat, so on and so forth. And I'm going to rotate it by some d phi. Okay. And let's do a Taylor series expansion of this, okay? Let's do a Taylor series expansion of this. And we're going to first write this out in a weird way. I'm going to write this out as if I'm doing compounded infinitesimal rotations, right? So I do one infinitesimal rotation, then I do another one, then I do another one, then I do another one. So that compounding of infinitesimal rotations is really equivalent to a whole rotation, right? Now I'm just going by little discrete chunks, okay? So how do I want to write that? I write that in the following way. So now my dz of phi is going to be taken in the limit as n goes to infinity, right? My number of iterations. And I'm just going to compound this operator that I've constructed. And now I'm going to do it in the z direction, right? Because now I've labeled it as z. I have an h bar. I have a phi over my number of iterations. So first I'm just putting this into a more approachable form, okay? So now this represents compounded infinitesimal rotations, right? And now I'm going to Taylor expand this, or power series expand it, whatever you want to call it. kz phi over h bar. So now I'm just doing some algebraic manipulations to get this in a nicer form. Oh, exp just means e. I don't know if you've ever, it's just the number e. So that gives me a 1 minus I jz phi over h bar minus I jz squared phi squared over 2 h bar squared plus higher order terms. Okay, so that's my typical Taylor series expansion. And now let's take the commutator. Let's take the commutator. So now I have an object for jz, infinitesimal, compounded measurements. The fact that I'm taking the infinitesimal limit as n goes to infinity means what? It means that this infinitesimal rotation really becomes a continuous rotation, right? Now this is becoming a continuous rotation over my parameter phi, right? So that's why this d phi drops. There's no more d phi because now it's some continuous angle. It's not an infinitesimal angle because I've compounded my rotation by some number of iterations. Does this all make sense? If it's a little confusing, ask now or ask me tomorrow, because this is abstract mathematically. It's a little you have to wrap your head around it if your calculus intuition is not the best, which is okay. Okay, great. Okay, so I can now rewrite jy and jx in this form. Okay, and the reason I did this is it's going to give us a nicer form to write down our commutation relation for angular momentum. So let's just take the commutator now. I'm going to erase this, and I'm going to rewrite jx and jy in this form, and I'm going to take the commutator and see what I get. Okay, let's do it. Okay, 1 minus I jx, where is, no, epsilon. I'm just going to use epsilon again. Okay? So this is just the same commutator, just written in this new sort of iterative form. We'll call it the iterative form. And when you work out this nasty multiplication, you get this. Okay, so now we've derived a commutation relation, okay? And in the infinitesimal limit, obviously. And we can write this now as this. Jx, jy equals I, h bar, jz. And you can work out the algebra. But we have derived now a commutation relation. If you didn't follow any of that, it's okay, as long as you understand what I just wrote down here, because this is the takeaway. This was the derivation. Now we know that our angular momentum comes in multiples of h bar, right? So we got an h bar, which is good. And we also know that angular momentum doesn't commute, which makes sense. It's what we expect. Give you a second to write that down. Okay, can I erase? Okay. Okay, so now we have a commutation relation, huzzah. And now I'm going to generalize this, and I'm going to introduce you to your first interesting object that we're going to use a lot. So, okay, so why did I go through all that? I went through all that to show you that we can use something classical, the rotation group, and we can derive a quantized commutation relation if we go in the infinitesimal limit, right? That's why I went through that process. That's why that was important. But now let's generalize this into something very great, which you're going to be using a lot. So now if I want any arbitrary direction, ji, jj, little j, where I and j run from 1 to 3, I get this object. I get I h bar epsilon I j k j k. That's the general form, where epsilon ijk is the Levi-Civetta tensor, which is a completely anti-symmetric tensor, which I think Gabe went through from your last problem set. And this is an amazing object. This is the Lie algebra. This is what we call the Lie algebra for angular momentum. It's a celebrated object. Lie algebra for J, angular momentum. And so Lie was a mathematician, L-I-E, and Lie discovered this Lie algebra. We call these things algebras, by the way. So anytime you have a set of commutation relations, it's called an algebra, okay? So Lie discovered this by doing exactly what we did. Taking an infinitesimal limit of rotations and taking them in the, in that limit, and then he got this Lie algebra. You guys know how this Levi-Civetta thing works, right? Okay, so time to ask you then. What is epsilon 1, 2, 3 equal to?
1.
We'll go around the room. No, we're going to go around the room. I can't really see your names. Johnson, what is, I can pick on Johnson because he's one of my good buddies to lighten the room. So what is epsilon 1, 2, 3 equal to?
I believe it's an even permutation, so it should be 1.
1, exactly. What is epsilon 132 equal to? Kelly.
-1?
Exactly, -1. What is epsilon 112 equal to? Rika.
0.
What is epsilon 112 equal to?
Is it 0?
0, exactly. It's okay if you get it wrong, it's not a big deal. Okay, what is epsilon 213 equal to? Lizzie. She might not be.
Not sure.
It's okay. Someone want to help her out?
-1?
-1. Okay. We'll do 2 more. What is epsilon 312 equal to? Julia. Oh no, there is no Julia. Jenna. Sorry.
I don't really know the difference. Like, I don't know what an even or odd permutation is.
Okay.
I just know if it's even, it's 1, and if it's odd, it's -1.
Okay, so this is 1. So I'll tell you the trick, ready? I know people use even and odd permutation. It's fancy words. There's really a really easy trick. You always start at 1, okay? And if it goes in order, 1, 2, 3, it's 1. If it goes out of order, so in this one, we went 1, you start at 1, you go to the right, it goes 1, 3, 2, so it's not in order, so it's -1. That's it. And if you have 2 indices that repeat, it's always 0. Does that make sense?
Yeah.
So let's say we have epsilon 3, 1, I'm running out of combinations, but 2, 1, 3. I don't think I did that. No, I did that one. Anyways, you get the idea. Does that make sense? So that's the trick. It's just sort of you start at 1, and if you're going in order, it's 1. Okay, that's what we mean by even permutation. This doesn't hold true when you get to 4 indices on the Levi-Civita. Then you might have weirdness, but we're not going to use that now. We're going to use that. We're not even going to use that for QFT. So this object, these are called the structure constants. Okay, so now we have the algebra for angular momentum. Okay, and you're going to see in quantum field theory that we're going to use a lot of Lie algebras. For example, when we describe the theory of the quarks, which is an SU3 theory, we're going to have a Lie algebra for quarks, and the structure constants will be like this, some F, A, B, C, and in this matrix, you're going to have a bunch of colors or flavors of quark. Okay, so I mean, this is going to come back to haunt you if you don't like it now. I'm just saying. Okay, great. Okay, now let's make this a little bit less abstract. Okay, I feel like we've been a bit too abstract so far. We've gotten something really tangible. We've gotten a commutation relation. We've gotten a Lie algebra. If you want to read about Lie algebras, you should read Z. Book by Anthony Z-E-E, Group Theory. There's a PDF online. Group Theory in a nutshell for physicists. And you can look at chapter 1. And he uses the rotation group to get a Lie algebra, just like we did. He does it a little differently. And he tells a nice story, too. Okay, great. So I'll just write it again, just so we have it for reference. And now we're just going to go crazy and derive a bunch of commutation relations. Okay, great. But before we do that, I want to make this a bit less abstract. This is like really abstract, like what is J, right? What is J even doing as an operator, right? How can I more tangibly define J? And to do that, we're going to use our Schrodinger differential operator representation, because I think that gives a much better sort of physical picture. So let's go to our classical relationship that L equals R cross P for angular momentum. And so what do I mean by this? I mean that Lx, so angular momentum, I'm using L and J sort of interchangeably, okay? So L and J is both angular momentum. This is the canonical form for quantum mechanics. So Lx is equal to y pz, these are momentum components, minus zpy. So now I'm just taking the cross product. Ly equals zpx minus xpz. And Lz equals xpy minus ypz. Okay, and this is just the cross product. So now we're getting a bit more of a physical view of what these operators are doing, right? And now why is that? We know in quantum mechanics that P, momentum, and I know you guys like the hats. You know what? I'm just going to go crazy with the hats. There we go. This is for all you folks that love hats. There we go. Everything is a hat now, okay? Because these are operators, the J's. They're Hermitian operators. They're orthonormal. They're everything that we have described. And everyone loves hats. So now you know why I don't use hats, right, Kelly, all the time? Because this is going to be a big mess in a second if I keep writing hats. Okay, but we know what P hat is, right? Like P hat has a physical differential operator form, and that's just H bar over I nabla, right? I mean, that is the form of P hat. Oh, have any of you seen this before? Okay, so so by the way, guys, calculus is not just one dimensional, right? You get to multiple dimensions. So all this nabla is okay, I should just describe it then. This is called the gradient operator, right? And nabla, should put an arrow because it's a vector operator, is just equal to a partial derivative in 3 directions. And of course, I'm working in a Cartesian basis, so it's del del x, del del y, del del z. If I was working in spherical coordinates, this might be totally different, depending on my basis. And this makes sense because the momentum operator in 3 directions, should put an arrow, well, let's just look at P hat in 1 direction, right? So P hat in the x direction is what? H bar over I del del x, right? So now in 3 directions, it's just three objects, x and y and z. So we know what this is. So now we can write out our angular momentum operators in a more physical way as real differential operators. So let's just do that, just so we can get that in a nice form. Okay, so we have that P hat, P vector hat, I should write, equals H bar over I nabla. And so let me just rewrite all my angular momentum operators in a more physical form. So I can pull out an H bar over I have a y d dz minus z d dy. And I can do the same for Ly equals H bar over I just factor that out. Where is it? Z d dx minus x d dz, and I can do the same for LZ. Don't tell me I erased LZ. No, I didn't. Thank God. I didn't remember it. So H bar I x d dy minus y dx. Okay, so hopefully this gives you a more physical view of what these operators are actually doing, right? Instead of that sort of abstract kind of way, which is not even really useful, to be honest with you. You're never going to be using infinitesimal versions of these operators. You're going to be using this version to do calculations, right? So if I want to derive more commutation identities, which you'll do in your homework, use this version, right? Because then it's just a matter of multiplying things. Okay, so I'll give you a second to write that down, and then we're going to just derive a bunch of identities, and we're going to build up the angular momentum algebra even further. Any questions? Okay. Okay, so let's take a 5-minute break till 10:30, and then we'll spend the last half an hour plowing through a bunch of identities. So get your arms ready, because it's going to be a lot of writing. Okay? I'll give you guys a 5-minute break.
I do have a question about earlier. Like,
Sure.
it was a while ago when you did like the power series expansion, and then you like for the rotation operator, and then like you kind of truncated it to epsilon squared, right?
Yes, yes. I chose to ignore order epsilon terms.
Oh, okay. So I mean, I can see, in classical mechanics, you do that a lot, and then like the epsilon cubed or whatever, they're just basically negligible. But I would have thought that in quantum mechanics, like those are.
You're very right. You're very right. I'll tell you something now. If you do that computation only to order epsilon squared, they commute.
Oh.
So do the computation only to order epsilon squared, they commute. Now I've taken a lot of liberty in where I truncated, what I cut off, but I've dropped all terms of order epsilon, right? And I've dropped all higher order terms in that series. So you're right. There is some stuff missing. In classical mechanics, you'll do the same. There's no funny business about what terms higher order terms you can cut off in classical mechanics versus quantum mechanics, because epsilon is the same, right?
Okay.
Right? And so like it's going to be small in either regime. It's not like just because we're working in a smaller length scale, epsilon is somehow treated differently. Does that make sense?
All right. So being able to cut off higher order terms holds for either regime.
Yeah, we're still treating it as a really tiny parameter.
Okay.
Regardless, I know sometimes that's weird, right? Because you're like, oh, there's an H bar there. That's really tiny, so epsilon might be bigger, but no, it's always an infinitesimal parameter. Does that make sense? And you're very right in saying that I've taken the liberty in truncating it at a certain point. I have, because if you just look at epsilon squared, they commute. So I didn't mention that because it's more of a subtlety of the computation, but that's a good catch. So I'm thinking I might have everyone just present their final paper instead of having a few classes at the end. I think that would be better, but we'll see how much stuff we get done. The fact that we started in August means that we've gotten a lot. We're very ahead for only being in the middle of September, so which is good. Has the school year started for you folks around, it has? So are you totally online or are you in person? What's the?
For me, we're totally online.
You're totally online? What about you, Jen? Are you online or in person?
Yeah, we're fully online right now, but my school is thinking about doing hybrid in the next few weeks.
Nice. What about you, Karina? You're not in the United States, right?
I am. I'm fully online too.
You're online too?
Yeah.
Nice. You know, I live in a very conservative part of New York. It's like a suburb, and we're not online because they're very Johnson. Because he's my neighbor. He's home too now. I'm home because of the virus. Get that applause off. We should be online.
Yeah, the school I have a 7-year-old brother, and the school he goes to somehow is in person, and they had someone test positive for coronavirus the other day. So like,
And you're in California, which is super liberal, and
yeah.
that's crazy. Okay, let's get going. So now it's time for rapid fire commutation relations and identities. Except not so rapid fire, because we're going to define some very important objects in a very specific way. Okay, so let's write down the first identity. J hat I in any direction times J squared of my angular momentum operators commutes. Okay, you can work that out. That's kind of an interesting one. Now I'm going to define two operators in very specific ways. So this is J plus. This is going to be called my raising operator. And you might be like, why are you defining it in this way? This is so weird. It's because when we work out the commutators, we're going to get a very interesting use out of them. And J minus, J hat minus, is equal to J hat x minus I, J hat y. Johnson, just curious, when you took your version of quantum mechanics for engineering people, did you use these kinds of objects?
No.
No, okay, good. Okay, so now I have this identity, just playing around with these raising and lowering operators, that the Hermitian conjugate of one gives me the other, which makes sense, right? The sign just changes. Okay. So this is the raising, this is the lowering. And the promise I made to you was we're going to have some spectrum of eigenvalues for angular momentum. This is going to take me up a rung on the ladder. This is going to take me down a rung on the ladder. So it better work out like that. Otherwise, we're going to have to redefine our raising and lowering operators. So let's try it out. So let's just work out some relationships. So let's do J plus times J minus. And again, I'm just skipping so much algebra, but I trust you can do it. Check my work. Please check my work. Jy squared minus I times this commutator. Okay. Equals J hat x squared, J hat y squared, is h bar, J hat z squared. And these are just going to be useful sort of tools and combinations that we're going to need. No new physics here, really. Okay, and similarly, J hat minus times J hat plus equals J hat x squared plus J hat y squared minus h bar J hat z squared. Can I drop the hats now? Is that okay? Okay, let's keep going. If I just keep playing around with this, I get that the commutator of J hat plus, J hat minus is equal to 2h bar, J hat z. Okay, now I'm going to write down another identity. J hat x plus J hat y squared equals J hat plus J hat minus h bar J hat z equals J hat minus j hat plus minus h bar j hat c. Okay. Great. I'm going to define j squared in the following way. Okay, and this gives me an important relation. Like if I take the commutator of any raising or lowering operator with j squared, I also get the fact that they also commute. Okay. It's a lot of algebra that went into this. So please check it. I'm almost certain there's some sign error here. Give you a second to write all that down. Really no physics here, it's just a bunch of algebra, right? Where the motivation has been sort of spelled out pretty clearly. Okay, can I erase? Okay. Is this size readable from your screen? Okay, yeah, I like to write smaller so I don't have to erase as much, but I wasn't sure how it looks. So I think I'm gonna stick to this size. So if someone has trouble seeing, let me know, I'll just write bigger. It's fine with me. Normally when I'm working something out, it's even tinier because I don't want to erase anything, so. Okay, so let's work out the following then. Let's see what JZ does, what J plus does to some angular momentum operator. Okay, so now I'm just using the definition I just wrote down. And I need to work out all this algebra. And I get the following. Let me make sure I did this right. Yeah, that's it. Okay. So I get this out. So I get that operator, my raising operator, back by some multiplicative constant h bar, which is good. But I still have not manifested how this is taking me up an eigenvalue, although I can kind of see where we're going. Okay. So let's just keep molding this a bit more. So now I want to define the following bracket with two values, j and m, okay? Where j and m are real numbers. So now we're going to get to the real angular momentum bit. And I want to call j and m two eigenvalues of angular momentum. For any of you that have ever looked up angular momentum quantum mechanics, you probably see a ton of j and m's everywhere. And for a long time, when I was in high school, and I was like, I want to learn angular momentum addition. I looked it up, and I'm like, oh, the M is a mass. No, it's not a mass. It's just another eigenvalue. So poor little Kyle, freshman in high school, was very confused because he saw a bunch of M's everywhere. And then quickly realized that the M's could not be a mass because the computations made no sense. So the M is just another eigenvalue. I don't like that we use M. We could have used some other number. But it turns out we're going to be using these kinds of functions a lot. Y upper LM. These are called spherical harmonics. And it's just these M's keep coming up for some reason. So they don't really care that particle physicists usually mean mass. Okay. And now let's see what happens when I act some of my operators on this ket, okay, on this state, okay? So let's see what happens. If I act J squared on this state, okay, I get H bar squared J plus 1 Jn. Okay. Yeah. So can someone tell me what just happened here when I acted J squared onto this state of eigenvalues? What's going on? You can work out all the algebra, obviously, but what's going on? Like, what is this telling me? First of all, I'll ask you the simple question. What is this operator actually acting on? What is it doing? Is it changing my M eigenvalue or my J eigenvalue? Changing my J eigenvalue, right? Little j, okay? Because it's moving it up the ladder, plus 1. Why do I have a J squared here? That's a kind of interesting thing. You do expect a J squared because this operator is J hat squared. So you do expect a J squared, but you don't expect this sort of combination, right? You would just expect a little J squared, Jn. Right? That's what you would expect. So this is kind of weird, but you'll see that it doesn't actually matter in the grand scheme. So let's just keep playing around with this. If I just act a single operator, onto J and M, so if I act JZ, you get this. I get that I go up an M eigenvalue instead of a J eigenvalue. And so I can get the following relationship going from one eigenvalue, one set of J and M angular momentum eigenvalues to another. I just get a set of Kronecker deltas. M prime, M. Which makes sense, right? Because they're the same except for the multiplicative constant. Does that make sense? So in other words, they're the same, they're just separated by the same value, right? So M is equal to 1/2, is equal to M prime, is equal to M double prime, right? But how am I sort of, I'm always going up by values of 1/2, right? I'm always going up by the same value. So this makes sense mathematically. Plus our inner product always needs to be 1 anyway. Okay, that's kind of, that doesn't mean that these two things are 1, right? It just means that the inner product's 1 because these are Kronecker deltas. Okay. So let's think about this now. So I kind of have a relationship between the raising operator, the lowering operator, J squared, and JZ, right? I have a relationship now between those 4 objects. Now, what's very interesting is that I could have used any direction. I just chose JZ because that's what's done. That's what's done sort of just normally. We just choose Z. But you would get the same result for any direction. Okay, let's keep going. I have the following condition. This is just a normal physics condition, that this set of eigenvalues must be greater than or equal to 0. Okay, so I can't have negative angular momentum. Let's play around with this some more. Let's use our raising and lowering operators and see what happens now, okay? Which is the key. So if I take J squared and I create an object of this, construction onto my state, I can change this order, doesn't matter. In this context, you can't always do that. I can rewrite this as this. So now I have two operators acting onto my angular momentum state, set of eigenvalues, and turns out when you work out all algebra, you get this. H bar J plus 1, J hat plus minus, onto Jm, which is fine. That's what we just wrote. Let me just make sure. Okay, good. Yes. Which is good, which I've achieved what I've wanted. And let me just put it this way now. The reason this thing is here is because if you work out the algebra, it's going to get rid of one of these J's. Am I frozen? Okay. It's going to get rid of one of these J's. So work this expression out for a raising operator and see what you get. See if it's raising J up by one eigenvalue, raising M up. Okay, but let's work out this following thing now. Let's work it out with JZ. And this one's going to be a bit more tricky. I'll work it out explicitly. Plus on the state Jm. Yeah, so this is just the state. One. Okay. And we get this final expression, which is important, which is really important to understand. So I'm just, I'm just acting the operators based on the definitions we just used. And I mean, this is just not a big deal. But what is a big deal is this. Okay, I'll let you write all this down, but I'm going to explain what this is up here. So basically, when you work out the algebra, it's very tricky, it's a little abstract, but I'm going to give you the whole physical intuition now in a few sentences, okay? So here's the basic idea. the idea is we have two sets of eigenvalues, J and M, right? And why do we choose two sets? It just happens to be a convenient choice, right? It's like, why do we choose A prime, right, in our measurement algebra? Why don't we just have one A prime? Well, we'd like to see repeated measurements, right? So it's similar to why we choose two sets of eigenvalues. One operator is raising the eigenvalue on the ladder. So I'll just draw this explicitly. So I have some ladder of states, right? I have my M side and my J side. Let's just say this is J1, and this is M1. And this is M1 minus 1, and this is J1 minus 1, right? And this is J1 plus 1, M1 plus 1, M2 plus 2, and J2 plus 2, right? So I have a ladder of eigenvalues, right? And I want to go up and down the ladder from one to another, right? And that's separated by H bar, okay? I use a raising operator to go up a rung from any arbitrary J or M eigenvalue. I use a lowering operator to go down a rung. That's all of this stuff is saying, and what you need to understand. So I've written that down here. If I have a raising or lowering operator, it's plus minus because it could be either one. It's going to move one of these eigenvalues up or down. I chose M, you could have chose J. Doesn't matter. It just depends on how you want to write it. This is a constant that's equal to this. The reason it's equal to this is when you work out the computations, you're going to need this constant out in front to make sure you move up exactly one or down exactly one for either eigenvalue. This is what we call a Clebsch-Gordon coefficient. By the way, this is all very abstract because you have to work out the algebra. None of this is going to make sense if you're just reading it, and you know, it's one of those things where, let me just write this down before I go on my rant. It's one of those things where you need to work out the math, okay? You need to work out the math. But what I will say is if you don't work out all the math, it's okay. Just know the principle behind it, okay? Because when we get to field theory, we're going to be moving up and down, not like this. It's going to be easier. This is actually a little cumbersome. And really, people don't do it like this anymore. You just need to see it once, okay? So don't get too worried if you're like, what's going on here? It's okay. Just get the general principle, work out all the algebra if you want, and just make sure that it's moving you up and down the ladder. Okay, and I've sort of given you all the identities to do it, okay? Okay, great. So now I'm going to take our results and I'm going to turn all my J's into S's, and I'm going to call the S's spin operators, okay? And we're going to talk about spin. We're going to do what we call spin decomposition. And hopefully it's going to look a bit more concrete when we start working with real numbers. Does that sound like a plan? So let's work with spin 1/2, okay? Where now our J and M's are defined. They're 1/2, right? Because now they're spin values. Spin is also a kind of angular momentum, right? Spin is the kind of angular momentum that corresponds to this, like we discussed, right? So it can fall into this picture. So let's do it. Okay. What will be way more crucial is the use of raising and lowering operators for the harmonic oscillator. That will be way more crucial, but that's a much more straightforward idea. Okay, so let's just write out the algebra for spin. It's exactly the same as the algebra for L, except now everything magically becomes an S. What am I doing? Okay, and we have the same Lie algebra. Okay. And we have the same raising and lowering operators, except now I call them S and M. This is just what we did. And we have the same definition for raising and lowering operators. Okay, and now, except now our spin values come in half integer quantized quantities. Okay, so now we have some numbers that we're putting to it. So we'll deal with half integer spin. All the particles that make us up are spin 1/2 and spin 3/2, and not spin 3/2. Yeah. Okay, fine. All of the particles that make us up are half integer spin, and those are called fermions. Okay. All the particles with whole integer spin are called bosons. So the force carrying particles are whole integer spin, photons, the Higgs boson. You guys have definitely heard about that. Those are all whole integer spin particles. Okay. And spin is a kind of angular momentum eigenvalue, right? It's intrinsic angular momentum. You know, there's a very funny video where a physics undergrad asks his professor, what do we mean by spin? Okay. And then that same student in graduate school asks his professor, what do we mean by spin? So it's a very confusing idea, but I mean, suffice to say that we kind of know how it behaves. Okay, great. So this is just everything we've been doing. We have our algebra, we have our commutators, we have our angular momentum relations. If you just remember this board, you don't need to know anything else. And if you go on Google and you look up what the hell's going on here, you know everything about angular momentum. Okay? I just showed you the algebra just so you've seen it. Now, the last thing I'll show you, we can describe this little column matrix with two components, column vector, and we can call it, and also I should write here, we're going to have these kinds of eigenstates, right? Or we might have a spin down eigenstate, right? So when they're in the positive direction, we say it's spin up. We have a negative spin, we call it spin down. Okay, so this would correspond to our electron, right? You maybe saw this as some h bar over 2, right? I just set h bar equal to 1, so okay, so I can create, so what do I mean by spin decomposition? I'm just going to show you this very, very briefly. We could spend so much time going into this, and when we look at the Dirac equation in a few months, when we look at the Dirac equation, we're going to use these kinds of objects a lot. So no worry. So if I want to get a expression for any spin combination, I can sort of rewrite this as a matrix equation. And these two operators are called spinors, where spin chi plus is equal to 1, 0, and chi minus is equal to 0, 1. So these are called spinors, and I'm going to explain what they do. They're also a kind of operator, and you'll find that when we utilize these two component spinors on a basis, we can extract the correct eigenvalues of spin. I'm not going to tell you how exactly, because we're going to use these spinors a lot when we talk about the Dirac equation and quantum field theory, because these spinors are going to be very, very crucial to extracting physics. I just wanted to kind of show you how this works. Okay, so I would take a snapshot of this board and try and understand it, and then you know everything. In fact, you don't even really even need to know this, really this. And this expression is the most important, okay? And I encourage you to work out the math more in depth. I really went too fast, but we just don't have a lot of time. It's already 11, so I'm right on time. Okay, any questions? Logistics in general? Next time we'll be covering, we'll derive the Schrodinger equation. Actually, next week is going to be much more fun for you guys, I think, because it's going to be way less abstract. And we're going to do some real calculations. And I think next week, here, how about this? Let's make next week more interactive, okay? Because this week was so bad with all the algebra. Next week, I'm going to send out some of the computations I'm going to do, okay? And I just want you to look them up. You know, spend half an hour, look them up, see sort of how people do them, see how I do them, and let's have a little conversation about actually computing dynamics in quantum mechanics, right? Because we've sort of talked about discrete quantities, we've talked about continuous quantities now, wave functions, but now we have to put it all together because the whole point of physics is to calculate the dynamics of a system. So how do we do that in quantum mechanics now, right? And once we look at a few scenarios, then we're going to go to the big scenarios, harmonic oscillator and the hydrogen atom, which I got to tell you, the hydrogen atom, Gabe is there. Gabe, the hydrogen atom is a rite of passage, right?
It truly is.
It truly is. I mean, when you compute the fine structure constant, right, Gabe?
Yeah, I mean, you
When
can
you-
compute, yeah.
When you get that fine structure constant, right, that matches the lab to such a fine degree, and you can do it just with some quantum mechanics. Granted, you need some special functions, as Gabe knows, right? We're going to bring out our good old-fashioned spherical harmonics, right? I mean, you just start crying. You just start overfilling with joy. You get goosebumps on your, I'm kidding, it's not that extreme. But that's really, I mean, I just want to just have that in your rearview mirror. But these tools are extremely powerful, okay? I mean, we can really construct precise theories that really, really help us extract real measurable quantities. And right now, it's hard to see that because it's very abstract right now. But starting next week, it's going to get less abstract. Okay, we're going to start actually computing things next week. So we've built up all the machinery now. Now it's time to sort of do real physics. Okay? Okay, great. So as usual, I'll be available tomorrow morning. I just sit around from 9 to 10. So feel free to pop in whenever. It's just because it's my commitment I made that I do an extra hour to the folks that manage this thing. But you know, I'd rather talk to you guys, so do come rather than sit alone and, you know, just read something random. And you'll have a problem set this week. You won't have one for the 2 weeks after that for the research paper. And I might have the lecture after next week, have you guys kind of discuss with me. I mean, you should discuss with me your topic. Or if not, by the 26th, send me sort of a description of it, and we can chat one-on-one. Okay? All right, great.
Also, for I remember last week we sent you like an email if you wanted to join like a group chat.
Okay,
Do
okay.
you-
Yeah, so only you and Karina sent me an email. So I don't know, do you two want to be in a group chat together, or do more people want to be in a group chat? Because I only got an email from you two. So what's the feeling? We have more people here, so.
It would be nice to have more people, yeah.
Yeah.
I want to join. I just forgot to email you last week, and I just remembered during class today, so I'm sorry about that. But I'll do it.
No problem. Okay, what you should do now, okay, after I'm about to sign off, Gabe's going to take over. Those of you that want to be in a group chat, put your email in the chat here, and then one of you take the initiative and set it up. Is that cool?
Yeah.
Okay, because I only got 2, so maybe I thought, okay, maybe they don't want to. Okay, but that's fine. That's okay. You put your email here. This is sort of our finalized group, okay? Because I keep seeing the same people. So do that, and then, yeah, feel free to discuss your research projects. I don't want people working together on them, but you can discuss them, right? You can fight them out, and yeah, so feel free to do that. But I did get your email, but I only got 2. That's why I wasn't so fast to set it up, but okay. Okay, great. Thanks, guys. So I'll see you next week. Gabe, good luck. You have a lot of fun integrals to do.
Yeah, the integral sign, it's like, you know, it's almost like an F for fun.
Oh, they're so much fun. You just look at them and write down the answer. Like they're the best kind of integrals. Okay, all right, let me stop recording.